title of the module, Directed Graphs or Digraphs. In this module, we are going to study about a class of graphs called the directed graphs. Introduction. In mathematics, directed graphs are a way to formally represent a directed network, which is basically just a collection of objects that are all connected. In directed graphs, two vertices are connected in a very specific way. There is only one way to travel between two vertices. Digraphs are used to model pairwise relation between objects. Generally, directed network can be represented by a digraph. Many practical problems can be easily represented in digraphs. A directed graph is a graph that is a set of vertices that are connected together where all the edges are directed from one vertex to another. A directed graph is sometimes called a digraph. When drawing a directed graph, the edges are typically drawn as arrows indicating the direction as illustrated in the figure shown on the screen. A digraph D consists of a finite set V of points and a collection of ordered pairs of distinct points. Any such pair u, v is called an arc or edge or directed line. The arc u, v is said to have u as its initial vertex or the tail and v as its terminal vertex or the head. In other words, a directed graph D consists of a set of vertices v, v1, v2 so on up to vn, a set of edges e1, e2 etc. and a mapping xi that maps every edge onto some ordered pair of vertices vi, vj. Now we shall see some definitions related to the digraphs. Out degree. If V is a vertex of a digraph D, the number of edges incident out of V is called the out degree of V. It is denoted by d plus of V. The in degree, on the other hand, is the number of edges incident into V and it is called the in degree of V. It is denoted by d minus of V. Now we shall see some examples to study about the in degree and out degree in detail. Now behind me on this board, we have some graphs here. As you can all see, these are all directed graphs. You can see the arrow marks. So these are all directed graphs. Now let's start with the graph G1. You can clearly see that there are several vertices here and several edges have been marked, and different vertices have different edges. Some of them are having the edges incident upon them and some of the edges are going outwards of, for example, this vertex V2. There is edge E1 which is coming inside V2 and there is one edge going outside of V2. So likewise you can see that this vertices and the edges together they form a directed graph. And here let me show you how to calculate the in degree and the out degree of this graph. Let us take the vertex V1. Now for V1 you can see that none of the edges that incident upon V1 are having, none of the edges that are incident upon V1 are coming into V1. So the arrow mark is going outwards of V1 and likewise from V1 you can see this edge here also it is going outwards of V1. So V1 doesn't have, so d of V1 minus is actually 0 because there are no vertices coming into, no edges coming into V1. So d of V1 minus is 0 whereas d of V1 plus. So d of V1 plus means how many edges are going outwards of V1. So clearly you can see E1 and E3 going outwards. So the arrow is marked outwards and therefore d of V1 plus is equal to 2. And let us come to the next vertex, namely V2. So d of V2 minus means that we are going to calculate the in degree. So the in degree is there are two edges coming into V2. So you can see E1 going into V2 and E2 going into V2 and therefore d of V2 minus is actually equal to 2. but d of V2 plus, that is the number of edges going outside of V2 is, of course there is no edge going outward, therefore this is equal to 0. So as you can see, we have calculated the in degree and the out degree of these two vertices V1 and V2. You can calculate the in degree and out degree of the other vertices in this graph. You can try this on your own. Now let's go on to the next graph. So here you can see the graph G2, it looks like a it looks like a directed graph, except that there is one loop here. So at V1 you can see that this edge E7 loops inside V1 itself. So clearly this is not a simple directed graph, but it is a multi-graph which is directed, and therefore now in order to calculate the edge count, or in other words the in degree and the out degree of these vertices, we will be following this system. Let us calculate the in degree and the out degree of this vertex V1. So in degree is, as we know, in degree is the number of vertices going inside. So which means that here it is equal to, there is only one vertex that is going inside V1. See, when the vertex edge is looping inside itself, you take that the in degree count goes by 1 and the out degree count also goes by 1. So here for V1, how many edges are going inside V1? Clearly E1 is not going inside V1 and E3 is also not going inside V1. So the only edge that goes inside V1 is E7. Therefore, the in degree of V1 is 1. So what about the out degree? The out degree is the number of vertices going outwards of V1. So you have the edge E1 which is going outwards of V1 into V2, and you have the edge E3 which is going outwards of V1 into V3. So two edges are there which are going outwards of V1, and therefore the out degree count of V1 is 2, plus you need to take one more count of V1, because when it is looping on itself, it means that out of V1 the edge is again going outwards and going into V1 again. So which means the out degree count is also 1. Therefore it is these two edges plus edge E7, therefore the out degree is 3. So this is how you calculate when there is a loop in a directed graph. The rest of the vertices, of course, they follow the same concept. For example, for V2 the in degree is, you have one edge going inside V2, edge E2 also is going inside V2. Let us calculate the in degree of V2. So there is one edge E1 going inside V2, then there is edge E2 going inside V2, and there is edge E6 going inside V2, and therefore the in degree of V2 is 3. So d minus of V2 is 3. Whereas the out degree, if you calculate for V2, none of the edges are going outwards of V2, and therefore d plus, or the out degree of V2 is 0. In this graph, we just calculated the in degree and out degree of V1 and V2. There are other vertices too in this graph. So you can try them on your own. You can calculate the in degree and out degree of these vertices. Now let's move on to one other graph, namely G3. In G3, we can see that there are edges E3 and E5 going inside and outside of V1 to V3, and likewise here. This is not a loop actually, but these are parallel edges. This is also a different type of a multi-graph. So this is a multi-graph as well as a directed graph. Now how do we calculate the in degree and out degree of these types of graphs? Now let's consider V1. V1, the out degree is edge E1 is going outside of V2. The out degree here is also calculating E3 into account. So E3 is also going outwards of V1 into V3. Therefore the out degree of V1 is these two. So 2. So 2 edges. Therefore d plus of V1 is 2. And what is the in degree? So d minus of V1 is, can you spot the edge which is going inside V1? You can see that it is clearly E5. So E5 is going inside V1, and therefore the in degree of V1 is 1. Likewise for V4, if you calculate V4, you have V4, what is the out degree of V4? So there is only one edge here, E7, which is going outside of V4 into V5, one is going out here, and there is one more edge here which is going outside of V4 into V2, and whereas this cannot be counted as out degree because it is coming inside V4, therefore which is this edge and this edge, namely, therefore it is 2. Then you have D minus of V4, there is one edge, namely E6, which is coming inside V4, and then there is the edge E4 coming inside V4. Together the in degree of V4 is 2. Now there are several other vertices and edges in this graph. You can calculate the in degree and out degree of these graphs. Let us see some definitions related to the directed graphs. So we shall see the definition of a directed walk now. A directed walk in a directed graph is a sequence of vertices V0, V1, so on up to Vk, and the edges V0, V1, V1, V2, and so on up to Vk minus 1 Vk, such that Vi minus 1 to Vi is an edge of G for all I, where 0 less than or equal to I less than or equal to k. The directed path in a directed graph is a walk where all the vertices in the walk are all different. A directed closed walk in a directed graph is a walk where V0 is equal to Vk. A directed cycle in a directed graph D is a closed walk in which no vertices except the initial and the final vertices are repeated is called a directed cycle. A path or a cycle in a directed graph D is said to be Hamiltonian if it visits every vertex in the graph. So keeping these definitions in mind, let us see some examples. Now you can see that I have written 3 graphs on the board behind me. So let us see a V1, V2 walk here, and I have written the V1, V2 walk already. So V1 to V2, although there is a very straightforward path from V1 to V2, a walk is something where you kind of make a very aimless walk and you can traverse every vertex twice, thrice, any number of times. You can make a roundabout way and then reach whatever destination. So it need not be the shortest path. That is what is the purpose of a walk. So V1 to V2, although there is a very straightforward way to go from V1 to V2, I am going to take a walk. So I am going to be going across all the vertices and maybe repeat them and all that. So V1 to V2 walk. So V1, E3, V3, E6, you can see, you can follow them here also. So V1, E3, V3, so edge E6 to V5, and then edge E7 to V6, then from V6 through the edge E9 to V7, and through the edge E8 to V5, and then see you are repeating the vertex V5 again, and then maybe you are going to E5, E5 to V4, through E4 to V3, and from V3 to V2 I am taking the edge E2 and I am coming from V1 to V2. So let me show that again for you. From here I am going all the way down here, going here, here, and then going like this, here, like this. So this is the meaning of a walk. So you just take an aimless walk. The vertices might repeat, the edges might repeat. Of course, the edges can't repeat here because they are in a directed graph. So we are just taking an aimless walk here. So this is a V1, V2 walk. Whereas in a V1, V2 path, let us take another path here in the same graph. So I have written a V1, V7 path here, and of course in a path you shouldn't be repeating the vertices. So V1 to V7, you are going from V1, E3, V3, E6, V5, and then E7, V6, E9 and V7. So I start here, go all the way down here, and then V7. Obviously none of the vertices have repeated and therefore it is said to be a path. That is how the walk and the path differ. In walk the vertices might repeat, whereas in a path you are not supposed to repeat any vertices. So V1 to V7 path. You can even try this for any other 2 vertices. You can try to find a path between them, or maybe you can create a walk between them. You can do that as an exercise. Now let us see whether there is a cycle. We saw the definition of a cycle too. So definition of the cycle was, it is the starting and the end vertices are the same. So I have already written the vertex, the cycle here. So, V5 and V5, we start at V5 and we end at V5. So, V5 is here. So, you start here through E7, you go to V6, and then from V6 through E9 you are going to V7, and from V7 through V8 you are going back to V5. So, this is clearly a cycle, and of course, the edges are also cooperating with us. Suppose these edges were in different directions or on opposite directions, obviously we cannot be making such a cycle here. So, this is an example of a cycle. Now, let us go on to one more graph here, and now here we shall see a V1 V4 path. So, V1 to V4. So, V1 E3 V3. So, you are starting here, going here through E3 you are going to V3, and then through E4 you are going to V4. So, this is a very nice path. So, none of the vertices are repeating, none of the edges are repeating. So, from V1 to V3 to V4. Now, luckily for this graph we have a Hamiltonian path as well, because a Hamiltonian path is one in which it visits every vertex in the graph, but not repeating the vertices. So, it should repeat, it should span across all the vertices in the graph, but it should not repeat any vertices. So, that is the meaning of a Hamiltonian path. Although the Hamiltonian path might not exist in all the graphs, certain graphs if you are lucky you can get them. So, we are lucky here because for this graph G2 we are going to get a Hamiltonian path from V1 to V2. So, from V1 E3 V3 and then E4 V4, then you are going here. So, E5 V5, then E6 and V2. So, this is clearly a Hamiltonian path because you have covered all the vertices. So, V1 is covered, V3 is covered, V4 is covered, V5 is covered, V2 is covered. So, you have covered all the vertices in the graph, you have not repeated any of the vertices, clearly it is a Hamiltonian path. Now, let us see another graph maybe, and here also you can traverse. Why we have considered this graph is because there are parallel edges. Parallel edges are quite useful when you are able to traverse across the graph in a walk or a path. So, in G3 you can see that there is a V1 V2 walk here. So, V1 to V2, again very straightforward, there is a path. So, just travel across E1 and to V2 means that you are getting a path, but a walk need not be straightforward, it need not be short, you can take a roundabout way. Therefore, V1 V2 walk will go from here. So, V1 through E3 I am going to V3, then from V3 I am going back to V1 through E5. So, I am going like this and then I am going like this, and then back to V1 through E1 I am going back to V2. So, instead of going straight like this, I am taking a walk like this and then I am reaching V2. So, this is an example of a walk. Now, let us see a path. So, V1 to V2 path will be V1 E3 V3, E4 V4 and then E2 to V2. So, this is nice, it is a nice path from here to here and from there to there and here. So, this is a V1 to V2 path. Although it is not the shortest path, it is still a path. Incidence matrix of a directed graph. The incidence matrix of a digraph D with V vertices and E arcs is the V cross E matrix B equals Bij, whose rows correspond to the vertices and columns correspond to arcs, and Bij is equal to 1 if the jth arc is incident out of the ith vertex, and it is equal to -1 if the jth arc is incident into ith vertex, 0 if the jth arc is not incident with the ith vertex. Let us see an example now to construct an incidence matrix. So, here in this graph there are 4 vertices A, B, C and D. There are 4 edges as well, and this is a directed graph. I have already constructed the incidence matrix here, but let me show you how it is done. So, A, B, C, D, you take all the vertices on the left column. So, A, B, C, D has been written in the column wise, and then in the row wise you write all the edges. So, E1, E2, E3 and E4. There are 4 edges in this graph, therefore, I have written them row wise. Now, let us see A to E1. So, A, E1 is 1 because E1 is going outside of A into B. Therefore, likewise, we already remember, we should recall the definition of in degree and out degree. So, in degree you might have noticed that we use d minus, and for out degree we use d plus. Similarly like that. So, when you are seeing the out degree, or when the edge is going outside of A, it is plus 1, and if it is coming inside, see for example this edge A to D, it is actually this edge E3, it is going inside into A, and therefore the edge E3 is marked as minus 1 in keeping with that in degree out degree notation. Then E2 is also going outside of A into C, and therefore it is marked as 1, and then from A to E4, there is no edge between between A and E4, there is no connection, and therefore you can mark it as 0. For B we have you have E1 which is coming inside B, therefore minus 1. When regarding E2, there is no connection between B and E2, so E2 is not incident upon B, and therefore it is 0. E3, again E3 is not incident upon B, and therefore 0. E4 is going outside of B into D, therefore it in keeping with the out degree in degree notation, it is plus 1. So, 1 if it is going out, minus 1 if it is coming in. So, that is the notation we are using here, and so plus 1 minus 1 likewise. And then for C there is only one edge coming inside, and that is E2. So, E2 is minus 1. As for E1, no connection between C and E1, so 0. All the other edges E3, again no connections, so 0. E4 also 0. Now, let us come to D. D you have the edge E4 coming inside. So, E4 minus 1. So, that is what we have written here. Then there is one edge going outside of D, which is E3, and therefore straight to E3 you put 1. Therefore, 1 coming in, 1 going out. So, 1 and minus 1 here, and no connection between all the other edges. Therefore, it is 0 and 0 for E1 and E2. So, this is how you construct the incidence matrix of a graph, and you should remember that the incidence matrix is unique for every graph. So, from the incidence matrix, even if you construct a graph, you can perhaps get a slightly arranged, a very differently arranged graph, but they will either way they will be isomorphic in all counts. So, let us see how to construct a graph from the incidence matrix now. So, I have constructed I have an incidence matrix B here. So, all the vertices A, B, C, D written column wise here. Row wise we are having 6 edges. So, E1, E2 all the way up to E6. I am going to show you how to construct the graph from the incidence matrix. So, A, B, C, D, there are 4 vertices, and now let us look at E1, and then here that is minus 1. So, 1 and minus 1. A very easy way to do is, where there is 1 and there is a minus 1, clearly this edge E1 is going outside of A into B. So, you can mentally picture how it is done, so that it is easier to construct the graph that way. And E2 also, it is going outside of E2, so that is why it is plus 1, and then there is a minus 1 here, which means that it is probably going inside D, because for D it has become minus 1. So, it is coming inside D, so minus 1. So, and for E3 also very easy to see that it is going outside of, it is going to B. For B it is 1, and for D it is minus 1. So, you can make this mental connection here. Now, let us now start constructing the graph here. So, 4 vertices are there and 6 edges are there. Now, let me draw 4 vertices first. So, A, B, C and D. So, I have drawn, I have put in the 4 vertices now. Now, A, the incidence matrix says that the edge E1 is going outside of A. So, it is 1 here, and E2 is also going outside of A. So, like I said before, you just have to see here there is a 1, there is a minus 1, here there is a 1, and here there is a minus 1. So, clearly this edge E1 which is going outside of A is going into B. So, that is the connection that we make here. Therefore, it is going outside of A and into B. Then edge E2, and this is E1 by the way, let us do it immediately. E2 also here it is going outside of A, and correspondingly D is having -1, which means it is coming inside D. Therefore, this is the edge E2, A and D. Then the third one E3, here it is going from B, then here it is -1. So, E3 is either it is starting from B and going to D. And this is E2. E2 to E3 to starting from B and going to D. Yes. Next E4. E4 is again here it is -1 and 1, the rest are all 0, which means there are no connections between the other vertices. So, -1, 1. So, it is starting at C and going at D. So, going outside of it is starting at D and going to C, because C it is coming inside, that is why it is -1. So, it is starting at D and going to C. So, D to C. So, this is your E4. The next one here in E5, again it is going from B, it is going from C, because outwards means it is 1 and inside only it is -1. So, it is starting from C and then going to B, C to B, C and B. This is your E5, and then finally E6, it is 1 and -1 here. So, B it is going out and then going into C. So, B and C. So, which means that there is one more edge which is starting from B and going into C, like this. So, there is actually a parallel edge here. So, this is going inside and this is going outside. So, we have finished constructing the graph here. So, although you can rearrange the vertices and get a different graph, it will be still isomorphic to the original graph that we constructed. We can make different arrangements and all that, but the incidence matrix produces a unique structure. So, for any graph, the incidence matrix that we get is unique, and corresponding to a incidence matrix when you are constructing a graph, again you are getting a unique structure only, although when you are rearranging the vertices and all, you can get different sets of graphs, but they will be isomorphic to each other. So, the purpose of the incidence matrix is that we have made a connection between graph theory and an algebraic structure, because for a graph we have now given a matrix, which means it is given an algebraic structure which might be used to analyze the structure further. So, that is all for the incidence matrix. A digraph D is a tournament if its underlying graph is a complete graph. Thus, in a tournament, for every pair of distinct vertices u and v, either u comma v or v comma u, the ordered pair, but not both, is an arc of D. The word tournament derives its name from the usual round robin tournament. Suppose there are n players in a tournament and that every player is to play against every other player. The results of such a tournament can be represented by a tournament on n vertices, where the vertices represent the n players and the arc u comma v represents the victory of player u over player v. Suppose the players of a tournament have to be ranked. The corresponding digraph T, a tournament, could be used for such a ranking. The ranking of the vertices of T is as follows. One way of doing it is by looking at the sequence of out degrees of T. This is because D plus of V stands for the number of players defeated by the player V. Another way of doing it is by finding a directed Hamiltonian path, that is a spanning directed path in T. One could rank the players as per the sequence of this path, so that each player defeats his or her successor. We now prove the existence of a directed Hamiltonian path in any tournament. You can see on the screen a tournament on 2 and 3 vertices. Let us see the handshaking dilemma. In a digraph D, the sum of the out degree of all vertices is equal to the sum of the in degree of all the vertices, each sum being equal to the number of edges in D. The sum of the out degree of all the vertices is equal to the sum of the in degree of all the vertices, which in turn is equal to m of D, where m of D is the number of edges of D. Let us see a problem. Find the in degrees and out degrees of the vertices of the digraphs shown on the screen. Also, verify the handshaking dilemma. The solution is that the given digraph has 7 vertices and 9 edges. The out degree of a vertex is got by counting the number of edges that go out of the vertex, and the in degree of a vertex is got by counting the number of edges that end at the vertex, which is shown in the screen now. The sum of the out degrees is equal to 9, which is equal to the sum of the in degrees, and which in turn is equal to the number of the edges. Hence, the handshaking dilemma is verified. Now, let us see some theorem statements. Interested people can go through the proofs in the script. The first theorem statement is every tournament contains a directed Hamiltonian path. The next theorem, let D be a digraph with an odd number of vertices. Prove that if each vertex of D has an odd out degree, then D has an odd number of vertices with odd in degree. The next theorem, the determinant of every square submatrix of A, the incidence matrix of a digraph, is -1, 1 or 0. Conclusion, let us recall the concepts of this session. In this session, we have seen some basic properties of digraphs like in degree, out degree, directed path and the Hamiltonian path with examples. Moreover, we discussed about the incidence matrix of digraphs, and also we saw some theorems related to the concepts we have discussed. I hope that this session was useful to you. Please do the quiz and the assignments in this module, because we learn mathematics by doing. Thank you. Conclusion for the entire course. We are at the end of this course, and this is the last session for the MOOC course on graph theory. In this course, we also covered most of the concepts of graph theory at the undergraduate level. In all these modules, we gave a detailed introduction of graphs with the types of graphs like complete, bipartite graphs, isomorphism of graphs, Eulerian, Hamiltonian, chordal and weighted graphs. Also, graph properties like matchings in graphs, distances in graphs, trees, independent sets, covering sets, planarity, connectivity and coloring. Further, we saw the applications of graphs like travelling salesman problem, Chinese postman problem and switching theory. Moreover, we discussed the algorithms for finding the shortest path and the minimum spanning tree. We hope that these sessions enlightened you about graph theory. Paul Harmos said that the only way to learn mathematics is by doing mathematics. To do problems, please go through the contents on the site, as it has some assignment problems that will help you to sharpen your problem solving skills. So don't miss your assignments and quizzes. It will help you to score high in your final exam of this MOOC course. I hope that you enjoyed learning this basic course of graph theory as much as we enjoyed making this course. We, the Educational Multimedia Research Center, Madurai Kamaraj University, wish that this course helps you to gain academic confidence in graph theory, and we hope that this course will serve as a shining beacon and inspire you to learn more about graph theory. Thank you for your support and all the very best for your future.